if there is a film at the surface that is say a few nanometers thick or something, it will be sensitive to, as long as there's some optical contrast. So essentially, when we're looking at optical roughness, what it's going to do is going to add a surface layer of lower index. So let's say that you had, let's say a silicon nitride film. So you have silicon nitride, your index is 2. If you had some roughness on that silicon nitride, say a few nanometers of roughness, by default, what we're going to do is we're going to put a surface layer above the nitride that has an index halfway between that and air, which is an index of 1. So then put a surface layer above that of, say, 1.5 index, essentially, and fit for a thickness. And that can correlate well in some cases. It's just...
But not like AFM.
It's not like, I mean, AFM is more of a, is it there, profile
Last
management.
year,
This can correlate
in
in some
December,
cases.
I attended one conference that MRS and you guys had one booth over there. So I talked to someone, they said, oh yeah, we installed it over here.
Oh, okay.
So they knew Dr. Koram.
Oh, cool.
So they were saying that this is capable for the roughness as well, optically.
It is.
So,
again, in...
because if we grow the thin film,
yes,
AFM, it gives the pattern like this, right?
Yes.
AFM. So the same thing can this tool also do, because our films are, let's say, few micron thick, and then surface roughness will be around like 100 to 200 nanometer.
Oh, that's very
right.
That's
Because 1 micron film will have roughness around like 100 200 nanometer.
Oh, that's quite rough.
Yeah, that's quite rough. Optically, that's quite rough.
That's very rough. So twofold. It's sample dependent. I mean, again, so your AFM is actually doing a profiling type of measurement. We're looking at how the polarized light moves. So the influence of a surface layer, as long as there's an optical contrast between that layer and what it's on, and if there really is roughness, as long as the roughness is much less than the wavelength of light that we're probing it with, so usually less than 1/10 of the wavelength of light or less, then it'll be optically rough. As far as it'll still look kind of specular to us. It's not scattering like you're grading. Okay. If you have roughness on the micron scale, same wavelength of light that we're probing, then that's going to be diffuse and scattering. So that roughness is just going to be more of a loss of intensity. So we're not recording that. But if you have roughness on the nanometers to tens to maybe 100 nanometers, that would also show up in the data. So if you really had a 2 micron film at 100 nanometer roughness, we would see that here.
So what we'll see is like a graph, like a scan,
No.
Linear scan.
No. So let's just do it here with this data right now. So for example, let me go back to fit here. So the data we were looking at here from the measurement we took last night was a thin film on silicon. It's a porous
thin film.
Porous thin film on silicon.
Transparent.
So currently we're modeling that with just optical properties of silicon, and we're fitting for the optical properties of that thin film using this Cauchy layer. Okay. For your amorphous silicon, you might have been using like a Towson lens or a coated lens oscillator. Same kind of comment, but we're figuring out the thickness of that layer and then the optical properties of that porous material. Now, if it was more porous, the index would be closer to the air, but it's got an index around 1.4 right now. If this material, we didn't try surface roughness, but we are currently doing a wide area measurement. The beam is, in this case, with that in there, probably 1 millimeter by a few millimeters, depending on what angle you're at. So it's going to average everything under that beam here. I'm not going to do it's not like AFM that you're going to have a lateral view of the roughness. Okay. So whatever the light interacts with, if there's roughness on the film, by default, you would add a layer called S-rough, or surface roughness. And what it's going to do is it's going to treat it as a surface layer of lower optical index. So what it's going to do is whatever my top layer is in my model, it's going to mix this with 50% of optical properties of that layer and 50% of air, or void, n equals 1. Now here you can be a little bit less sensitive surface roughness because my index is so low. There's not a lot of optical contrast between 1.4 and 1. If you have that nitride, or if you have your amorphous silicon or something that has a very, very high index, 2, 3 index, and that's much further away from the index of 1 than 1.4. So regardless, essentially, if you had some roughness here, we start adding it, we'll start to see some shift in the data here. Okay. So that we're going to be sensitive to fitting it. We didn't try to fit it in this case. I can try to see if that helps my fit. And in this case, it wanted a little bit of roughness, but I didn't show this a little bit ago, but we were hovering without roughness with an MSE or a fit quality around 20. for this particular model, we have no roughness. So in this case, it kept a little bit of roughness, but the MSE stayed very, very similar. So from our standpoint, it would not be justified to leave the roughness in this case. We want a large improvement in what this MSE parameter, this is a mean squared error, to justify the extra optical parameter. So in this case, if I included roughness in this model, twofold. One is my confidence limit is very poor. So this 90%, this error bar here is kind of the 90% confidence limit in the model of what I'm fitting right now. We like to, obviously you don't want to say, hey, my answer is 1 plus or minus 30. That's bad. We like to see whatever you're fitting, in general, to have at least the confidence limit be at least 10% or lower. So if it was really thinking there was 1.4 nanometers roughness, I would want to see plus or minus 0.14 or lower to have it more realistic. So it's trying to fit roughness, but it's not two things. The confidence limit was poor, and then this MSE value in this case is 19.5 versus if I just get rid of the roughness and I refit it with no roughness, 19.5. So I get the same fit quality with or without roughness. So in this case, I'm not sensitive to it in the model or doesn't want it. Now, if you really had optical roughness on this sample, this one just doesn't want it. Then, if I had included that and my MSE dropped it in half, then I would say, yeah, I'm sensitive to it. So there's plenty of papers out there for people correlating ellipsometric determined roughness with like AFM or MS or whatever, right? But it's sample dependent if it really has it. So again, if you have a sample that has roughness, I'd say just measure it. And then you can see if it correlates.
The problem with these films, it's not just the surface roughness, right? Because the film is
this porous, yes.
porous,
yeah.
and the pore sizes are large.
Yeah.
Then the roughness is going through the whole bulk.
Yeah, it's not just a surface condition.
Right, it's not just a surface condition.
So when ellipsometry is doing this optically, it's literally just adding a surface layer of lower index. But that's, if you add typical optical roughness, that's essentially what it does to the optical contrast, or optical properties. But what's your material that's a couple micron thick? What is the material? Your film?
Actually, mainly like the dielectric. Let's say if we grow the thin film from CVD, PVD technique, roughness is not an issue.
Yes. Over
there, surface smoothness is very good. But let's say if I do the silicon dioxide on silicon,
yes,
or like anodization, mostly I have seen whenever I do the anodization of aluminium, it makes the aluminium oxide, and then it makes some structure to be like rough and porous.
Well, anodization can also cause scattering too. So the easiest thing to do is just try it. I mean, measure a sample that you believe has how much roughness and one that has it, and see if the ellipsometer is sensitive to it, it'll definitely improve the fit to include roughness in the model. This particular sample didn't, but again, this was just what we measured. This doesn't want roughness. So I guess in general, so at least everything's kind of going through the isobar plug strip. Hopefully that helps. If you know you're going to have a planned outage, you can always just make sure to shut everything down. Just shut down. But turn off the software. Shut down the software. Go ahead and turn off the power to the boxes. That doesn't, or if you know you're going to have a glitch or something, you can just so the boxes aren't on when that surge comes. It should be fine in general. There's not much. If it happened during a measurement, it might. I guess the main thing I suppose if it happened during a measurement, you'd lose power to the vacuum, so your sample would fall. Typically, again, you can use. Sometimes it helps. Again, so the thing I was using as a shim when I wasn't realizing that 3D printed part was there. Again, that's a shelf. Sometimes if you're always mounting the same sample on there, you can mount this as a shelf, and then that sometimes stops it from coming. Again, in our lab, if you have a precious sample, because we do things overnight and everything, sometimes we add this like a little catcher thing, just like in case the sample falls and it falls into that. I mean, very rarely does it happen, but it can happen. You lose power. Similarly, this can only go up to here, but if you're always mounting a certain wafer size, you can slide that up and be a little shelf. So mainly the sample falling. If you have an incident, let us know. Okay.
The other thing is about maintenance. Like, what are the different things we should think about?
Sure. Again, the consumables, the lamp, I mean, really, it's a pretty low maintenance instrument. I mean, we've had these in the field for
Yeah.
a really long time. There's really not much preventative maintenance that I can think of. Over time, from that mirror, that reflector mirror in there, I think will be great. So, I mean, years, many years. But
Yeah.
sometimes people will get that replaced.
I see.
So mainly changing the lamp is the main thing. And just be careful with the optical fiber. So
Yeah.
again, that red fiber right there, it's pretty well where it is. But if you're don't try not to snag it if you're walking back there.
Yeah, nobody should be walking that side.
But in general, there's not really any PM preventive maintenance I can think of.
Okay. Okay, that's all.
Yeah, if we're done taking measurements, yeah, we can just turn off here. You can turn off the whole box if you want, but it doesn't need to.
Okay.
Again, if you want to save lifetime for the land, we just turn off. So again, if we're done for the day for measurements, I don't know. Again, we just turn that off. So your lamp is off.
Okay.
And then
This
tomorrow-
they go.
so you can leave everything else on. Yeah. That would be the only thing to turn off. You're welcome to turn everything off, but you don't really need to.
Sure.
Again, and if you turn off the software, you'll have to recalibrate.
But during a planned outage, we need to turn
Oh.
off the.
During a plane out,
controller.
I would turn everything off. I mean, even the computer, you don't necessarily
Yeah.
want
Yeah.
the computer just to
Right.
lose power just because why, right? Yeah, turn off the software, then turn off the box, turn off that box, turn off the computer.
Gotcha.
Maybe even turn off the vacuum pump, I guess. Doesn't as long as it's closed, it shouldn't hurt it. Again, there's an ISO bar there that should protect from a standard surge, but it's like I guess you gotta plug that
Yeah.
if you're like constantly having those things.
Of course. Yeah. No.
That'd be rare.
We don't have it very rarely.
Okay. Good.